Mm.
All right. Hi, everyone. Thanks, teams, for joining us. I'm going to be handing it over to our Reproducibility Challenge Chair, William Godoy from Oak Ridge National Laboratories, to kick off our Reproducibility Challenge webinar. Go ahead, William, take it away.
Thank you, Lemon, and thank you everyone in the SCC, the Student Cluster Competition Committee, for facilitating us in this seminar. So, as I might say, my name is William Godoy. Today, we're gonna kickstart with an overview of the Reproducibility Challenge. Let me go. All right, so what is a reproducibility challenge? First of all, it's one of the challenges in the student competition cluster, right? So we are, designed by committee, essentially. So this year I have the pleasure to chair that committee along with Taina. She had a conflict today, but we've been working along the way and now closer to the SCC. So please let us know if you have any questions. I put our contact information there. I want to also introduce the committee. Thank you so much to all the committee members that participated to get us to this point. I also put a link here on the description of the process. We had a blog recently published in the SC website, so you can learn more about how we get here and what is the motivation. So thank you so much. So what is the challenge? The challenge is, basically we get together, form the committee, and we select a paper from the previous year of the selected paper from SC24. And we also prepare the task and to reproduce the context. Basically, figures, trends in the results, things like that. But we try to make it interesting, and we also interview the teams. So our job is also to explain the process as we're doing that to the student teams. So expect us to be available at SC and also for the SCC and for the people grading the produced reports, the outcomes of the teams. So what we are asking for you from student teams is to prepare a report based on, this report is based on the SC25 artifact description, artifact evaluation appendices. We want to make it, we want to unify the format today. So I encourage you to read more about it. And, it's all available on GitHub. And, what we're really after is that you document your process. We are not so much interested at, it has to be perfect. But, if we have to give you a breakdown of what we're going to be grading is, well, first of all, the quality of the results. Make sure that you get where you got, with your data and code, 20%, but also the quality of the report. So reproduce figures, process, explain how you got there, make it interesting for your community, for the reader. And also, of course, the description of their environment and configuration. One important thing is that talk about your report when for example, here in section 1.1, and you see paper's main contribution. The paper's already been published, so, but instead of the paper, talk about, your report. You can, of course, cite the paper and, talk about it, but, make it about your process, what you spend the time on during the cluster competitions. I attach another resource, the Hallmeyer Catechism, which has very good points about how to write a proposal. Try to answer those questions before you even start writing your final report. And how do you communicate this to the people grading you? That being said, I want to first of all, congratulate and thank, the authors of the selected paper from SC24. Again, this was a selection from, close to 30 papers. And, this year we selected these papers in which Subaru will start talking pretty soon about, on asynchronous distributed memory parallel algorithms for influence maximization. So we pick a problem that, relate to us, related to social networks. I think the authors will do a much better job explaining the technical details. But, in the era of AI and, people talk about GPUs, they're not so accessible. So we selected, a problem that is still important because, memory movement is super important for where computing has been going, and it's going in as a major bottleneck. So we want to also get a custom of different aspects of, HPC. So that being said, I want to introduce you to Subhadra Hati. He's a four-year PhD student, computational science and engineering program at Georgia Tech under the supervision of Rich Budok. His interests focus on designing distributed memory, asynchronous algorithms, and irregular memory access, communication patterns. So also take advantage of the expertise that the committee and the authors are providing. He actually graduated from the Indian Institute of Science in computational biology, and he's actually completing his PhD at Georgia Tech. And also, let me introduce you to Subhendra Palsingal. He's also a co-author from Georgia Tech. He's a third-year PhD student in computer science at the Habanero Labs, Georgia Tech, led by Dr. Viver Sarkar. So his research interests include operating systems, high-performance computing, distributed runtime systems, large-scale parallel algorithms. So that being said, I have one more slide before I hand it to them. I just want to say thank you to the Student Cluster Competition Committee, Lemay, Abhinav, Student League. Their help has been invaluable for us to get here, and of course the entirety of the SC organization, and in particular the technical committee that we are part of, chaired by Amanda Randalls and Marty Schultz. So that being said, is there any questions for me? This just being a very high-level introduction, but so. No questions. If that, I'm gonna stop sharing and please, Subhadra, take it away whenever you're ready.
Introduction. I'm gonna start talking about some of the algorithmic aspect of the paper from last SC that is selected this year for the reproducibility challenge. Feel free to stop me at any point if something I say doesn't make sense. And once we go through the algorithmic side of things, my co-author Shubh will talk about how to use the code from the repository and the more important things that we need to know to be able to reproduce the figures. All right, so that being said, our paper was titled Asynchronous Distributed Memory Parallel Algorithms for Inference Maximization. So the problem that we are trying to address here is finding inferences. A social network can be modeled as a graph, but the question, who are influencers, is not easy. Colloquially, we can say it's a set of people that can trigger the largest expected number of follow-up adoption from the remaining society or remaining number of nodes from the graph. I'm denoting the node marked by S as the influencer here. More formally speaking, to be able to know if a vertex of the graph is an influencer or not, we need to find the activation set. So activation set of the vertex S here is all the vertices colored in yellow. We need to do that for a lot of vertices. And then we have to find which vertex is present in the maximum number of activation sets. Now, finding this we can reduce this problem to a very well-known computer science problem called the max cover problem, which is known to be NP hard, which in simple terms means there doesn't exist any algorithm that can solve that problem in reasonable time. Or if you can solve that problem, that automatically means you can solve all the other most of the other unsolved problems in computer science. So it is hard to solve exactly. So we need an approximation algorithm. One of the major approximation algorithm that performs well is this technique called inference maximization by martingale, where instead of looking into the whole graph and everybody's activation set, We take lots of sample from the graph, use the statistics from the sample to get an approximate outcome of the influencers. The algorithm looks like the pseudocode that I'm showing here, but the more important part from the HPC point of view, here are these two algorithms, generate RR and select seeds, which we talk about as kernel 1 and kernel 2. Reason being, these two are the primary computational part of this whole algorithm. They take practically the whole time in the execution of IMM, or influence maximization by martingale. Okay, so let's look do what we do in the kernel 1 that we call generate RR. So our goal here is going to be, we want to simulate how an information can flow in this input graph from a lot of randomly chosen sources. So what's going to be our steps? Let's pick a lot of sources. How many sources to pick is dictated by the rest of the algorithm, so we can ignore that important detail for now. But let's say we have selected all these 6 vertices from the graph. Now we have to perform random walks on the graph. Once we perform the random walks, we have achieved the activation set of these source vertices. And now we are going to collect the set of vertices that was part of each source vertices random walk as something called an RR set. We can simply think of it as a set of vertices that was part of a single random walk. Now, the problem about trying to do this for really large graphs is that a single compute node cannot store all the graphs, especially graphs of interest, which could be much larger in size. So we need to distribute this graph across different processors. Here, I'm giving a very small example of the same graph distributed among 3 processors, and let the color of a vertex dictate the processor it belongs to. So let yellow, red, and blue be 3 different processors where we are distributing the graph. The exact distribution looks much different, but for simplicity, let's assume this is how we are going to deal with it. Now we have 3 processors that the graphs are distributed in. We still have to do 6 random walks, like I discussed previously. One important fact here is that all these random walks from all these source vertices are independent of each other. So we can exploit this information to perform them in parallel without any conflict. So we can schedule all the 6 random walks simultaneously. Now, the challenge is when the graphs are distributed among processors, we just can't do a random walk like we're doing serially. We need to make sure each processor takes one step of the random walk or for the vertices owned by that processor. Then every processor synchronize and we repeat the step until all the random walks finished. So level 1, we select the source vertices. Level 2, we take one step. Level 3, we take another step. After multiple levels, when we reach the last level, all the random walks have been performed. And our goal is to store them distributedly among the 3 processors. This is the kernel 1. This way of doing this random walk by distributing the graph incurs heavy communication. That's why we're the first paper to approach this problem in this way, as opposed to distributing the graph. But for the reproducibility challenge point of view, kernel 1 stays same between the 2 software we want you to benchmark. So we can kind of ignore the performance implication of this kernel for now. The more interesting part happens when we have to mine these RR sets to find the influencers we care about. But before that, we need to talk a little bit about communication primitives. For those of you in the students who have taken a class in supercomputing or high performance computing or parallel algorithms before, you probably are familiar with these things. But for those who haven't, let's take a quick recap. And before even I proceed to that, I would just want to make sure if anybody has any questions, they can ask me now about everything I spoke before. If not, I will go ahead with my very brief introduction to collectives. I am assuming nobody has question. I'll just check. Oops.
So, Subhadra, just quick question. This is a time to not be shy. Ask as many questions as you can. You know, you have the author here, so. All right.
Okay. I mean, if you want to ask your questions at the end, that's also fine by me. I'm just checking points. Okay, collectives. Now, this is a busy slide, but let's try to think about the fact that we have 8 processors with processor ID 0 to 7 encoded in binary. So 000 to 111. And let's say they all have one number stored in those processors. Our goal is to find the sum of all these numbers at an efficient time where we can exploit the fact that we have P processors to perform the computation. How can you do so? The algorithm we'll be using is a very commonly used collective operation or communication primitive operation in HPC called the reduce operation. Now, before I walk you through the steps of the reduce operation, an important fact to note here is, suppose the processor 111 wants to send a message to processor 011. There is a computational cost of sending that message, which was not there in a serial processor. So the cost of sending a message of size m can be represented as tau plus mu m in a simple model, where tau, that term denotes the latency of the system, was the upfront cost you must pay when two processors want to communicate. And the mu term here dictates the cost you must pay per, let's say, byte of message being sent from one processor to another. Hence, if I want to send one message from processor A to processor B of size m bytes, I need to pay tau plus mu m cost. So tau and mu being two additional constant in the communication part of any algorithm is the additional term you must consider while trying to analyze a parallel algorithm. So anytime there is a parallel algorithm, using this simple model, we can get some idea about how efficient that is, how fast that's algorithm, and still in bigger notation. Okay, so now let's walk through the reduce algorithm. And our goal is to find the sum of number 1 to 8. So 1 plus 2 plus 3 plus ... 8. That's what we want to find. So the slide already has an arrow of messages to be sent described. So we are going to follow that. So all the processors from the right half of the processor, which means these 4 processors, send the data stored inside them to the processors in the left half. Using this communication called hypercubic communication. But to keep things simple, let's just assume all the processors in the right half is going to talk to left half, and we're just transposing them. So we get our partial sum operations. So we did one round of communication, and everybody sent one integer. So let's say 4 bytes. Now we are going to repeat the same process recursively. Now these 4 processors are what we care about, and the right half, so 010 and 011, are going to send 2 messages to 000 and 001. And we get some more partial results. We did 2 rounds of communication, and now our final result is partially stored between 2 processors, processor 0 and processor 1. Whatever I said before, we are going to repeat the same thing. So now we have 2 processors that we are going to only care about. So the right half, so processor 1, send the message to processor 0, and we get our final answer. So we had 3 rounds of communication. And initially, we had 8 processors. So if we had P processors, we'd end up doing log P round of communication. And all log in my presentation is in base 2. So log base 2 of 8 is 3. That's why we did 3 communication. M depends upon the size of the message. Let's say in bytes. In this example, I was only talking about single integers. So is O of 1 byte or 4 bytes, however you want to describe it. But I could also do the same reduce operation of large vectors. You could also imagine each processor had a length, 1,000 element or a million element length array that they all wanted to do a vector sum operation on. They would follow the exact same procedure here that I discussed for single integers to get the total sum. And at the end of this reduced collective, generally, unless we specify otherwise, processor 0 has the final output that we care about. So that's important to know. And I'm gonna stop after every slide of this communication primitive to allow question in case anybody has doubts, because understanding collectives is very important to appreciate parallel algorithms. Okay, I'm gonna move on. I'm assuming nobody has any questions yet. Now, in the reduced collective, what we did was each processor had one integer stored or some information stored inside them. We perform a reduction operation. Here, the reduction operator is a sum operator to get their final summation value in processor 0. There is a variant of that called all reduce. That stores the final output in all the processors and not just processor 0 by doing some extra communication that we did not do in reduce. So let's follow this algorithm step by step in this simple example. So initially in reduce, I said the right half send message to the left half. Here, we are gonna keep doing that. However, the left half also sends their message to the right half. So once we do that and we perform the local sum operation, both the first 4 processor and the last 4 processor have identically same partial results. And why that's good? Because previously in reduce, I said we started with 8 processor. After first round of communication, we were only looking into the first 4 processor. That means the first 4 processor and the last 4 processor are now independently working on the part of the same problem. So just like we discussed previously, the right half was always sending to the left half. Now in these partial problems of 4 processors each, the right 2 processors will always send to left 2 processor, and the left 2 processor will send their own information to the right 2 processor. So 10 and 12 will be sent from processor 3 and 4 to 0 and 2 and 3 to 0 and 1, and 0 and 1 will send their information to processor 2 and 3. So we repeat that, and that the same thing happened on the right half as well. So now see, previously, after 2 rounds of communication, only processor 0 and processor 1 had the final partial outcome of the sum operation we were trying to do in parallel stored inside them. However, when we expand the communication so that both the left side and right side both send their information, now every pair of processor has part of the final outcome stored. And if we follow the same algorithm that the right half sends to the left half sends to the right half, we have in every processor the final outcome of this sum operation that we are trying to achieve in P processors. Now, something to note here. If we had one processor that had 8 integer to store, it had to do the summation in order 8 step. And why I say order 8 instead of order P, just imagine the example talks about 8 processors, but in reality, we have thousands of processors. So if it's order P, where P is the number of processors, a linear way of doing this operation takes order P time. However, in parallel, we can expand this thing to make sure each processor first performs their part of the sum, which generally takes P by P, which is O of 1, if P integers are what we're trying to sum. And then we pay this additional cost of all reduce, which is log P time cost, additional to the local computation that you have to pay in communication to get the final result. So generally, while processing really large numbers, this communication cost ends up being negligible, and you get almost perfect parallelism in practice. Although in theory, they definitely have some communication overhead. Now this is all reduce. Just like reduce can be done on really large arrays as well as, let's say, vector sum operation or vector max operation. We can also do all reduce on really large arrays. So you had each processor stored, suppose a vector of length 1000 cross 1. You can do a vector sum operation in parallel perfectly, where at the end of the operation, every processor will have the sum of all the vectors using this all reduce strategy. I'm going to pause here again for a second to make sure anybody has any question or not. It's very important for you to understand how we enable computation in parallel. Oftentimes we use these collective operations to enable this efficiently. Otherwise, writing parallel code from scratch could be very hard. If I had to manually inject a communication from processor 0 to 1 every time I wanted to do a sum operation, that would not be productive. So these fundamental operations help guide how we design parallel algorithms. I'm gonna move on. Actually, the discussion about collectives more or less end here, because a lot of the communication pattern are exactly the same. Whatever we saw in reduce, we can now think of it, the reverse of it, as a broadcast operation. Suppose processor 0 has some information stored that we want to send to every single processor. What we are going to do is 0 is going to send to processor, 4, because we had 8 processor. 0, 1, 2, 3 belongs in the left half. So 0 is sending to the first processor in the right half. Now both 0 and processor 4, so both left half and the right half, the first processor have the output we want to somehow propagate to every processor. Once first step is done, now our problem reduces to first 4 processors and last 4 processors independently. We again follow the same trick. The left half talks to the right half, which means the first processor in the left half talks to the first processor in the right half in the second round that we can see here. And then the problem gets smaller down to just 2 processors, where the first processor among the 2 processors sends a message to the second processor. And by the end of this, all the processors would have this red color that we wanted to propagate. They didn't do an animation here. Important thing is we still do log P rounds of communication here. So if we wanted to do broadcast of any data that we wanted to broadcast of size M, I have to pay the same cost, tau log P for the latencies, because I am initiating communication log P times, and mu log P times M, mu log P, because I still have to pay the mu log P cost per byte of message I send, and I'm sending M bytes. Now, I discussed over 3 collectives so far, very briefly: broadcast, reduce, and all reduce. There is something called scan, which is a prefix sum operation. They all run in the same time, tau log P plus mu M log P. There are some more involved operation with more communication required, such as gather, all gather, scatter, all to all, and many to many. Now, the reason I am not gonna show how the algorithms for each can work in a different large size supercomputer is because it can get complicated. But I'm gonna give small intuition for all to all, or many to many. Let's say many to many. What operation we want to do in many to many is different processors has some data stored inside each processor that they want to distribute among all processors in a particular fashion. That's when we call many to many. Arguably, that's the most expensive of all collectives, because it's a very communication heavy operation. You are doing shuffle of information, large amount of information stored in each processor among each other. And that takes a lot of time. The runtimes are mentioned in the slides. I am happy to expand upon them if somebody wants to know more. And I'm assuming these slides will be given to you after this presentation anyway. So feel free to look at them and try to understand the cost of each communication operation as they become necessary while trying to analyze the rest of the IMM code base and the algorithms that you need to plot. Okay, that was a D2. Coming back to our happy world of finding influencers. What was the output from kernel 1 or generate RR? Was this set of vertices that were part of a single random walk that I call RR sets. You can store them explicitly like I'm showing on the right. And let's say we have 3 CPUs storing 1, 2, 3, 4, 5, 6 pairs of the RR sets, perfectly distributed among them. The same information can be stored in an implicit fashion. And to convince you I am not insane, let's take one example. So I've highlighted 3 vertices on the right, right? So vertex 12 of the graph is part of RR set 2, RR set 5, and RR set 6. So in the implicit notation, what we store is an array on top of vertex 12 of the graph itself that say, hey, you are part of random walk 2, random walk 5, and random walk 6. And if we do this for every single vertex of the graph, we can basically extract out all the information about which random walk had which exact vertex IDs. If this is not obviously clear, this is where you have to trust me and imagine and just trust me on the fact that the simple example of one vertex I showed is going to be true for both sides, and it's the exactly identical information stored differently. And why did we decide to use the implicit formation is the graph is already stored in some fashion among the processors. So the vertex were already partitioned among the processors. All we had to do was add this extra metadata to each vertex. So we found that a lot more usable distributed representation of this RR sets we generated that we need to process now. Okay. Now that discussion is out of this question, I wanna say, to make life a little bit complicated, I'm gonna pick either of the explicit and implicit version of the RR set as the input for the next kernel, as I seem suitable for ease of discussion. But know that they are the same thing. We are storing things in an implicit format more likely, more often than not. Okay. Kernel 2, the good stuff. We have these RR sets that were generated in kernel 1 via random walks. Now we have to find which vertices of the graph are influencers. And how do we do that? The approximate algorithm for max cover says, take a greedy approach. Find the vertex that's present in most of the RR sets right now. So we are going to do that. Happens to be 2 here, present in 4 RR sets. And select that your first influencer. So 2 becomes our first influencer. What do we do now is we remove every single RR set that 2 was part of and repeat this process till we find our K number of influencers, where K is the input query of influencers. So next time we find that 3 is the next most influencer set, because among the remaining RR sets, 5 and 6, 3 was found in both of them. And in reality, we'd have so many of these RR sets, we are not going to exhaust them all. In this example, I did exhaust them all, but we repeat this K times till we find K influencers, and we are good. We found our influencers. So how do we approach parallelizing this?
Well, I have a question.
Yes.
In your previous slide, you also have number 10 over R1, R6. So should that be selected too, or it has more?
So R1 to R4 have been already removed. So whatever I did, because 2 was selected as influencer that was present in all 4, we now remove those RR sets from our data. So they all told us 2 was the influencer that we feel, assuming that's the most common influencer here.
Okay. So you go from highest and then you remove and then you go to the next level. Okay.
It is a very greedy strategy. So just find the highest present right now, whichever RR set, whichever set it belongs to, remove those sets from your input collection, and then repeat the process in a recursive fashion, still greedily.
Got it. Okay, no, thanks. That answered my question. Thank you.
Okay, so how do we do the same process in distributed memory? So the first algorithm is the actor IMM selects this algorithm. Or to make life easier, let's start calling it actor IMM 1D, although the paper does not explicitly say 1D. So like I said before, the RR sets that I'm showing here on the left side can be stored implicitly, like I expressed here.
Sorry, there's a question sorry to interrupt you, Safadra. There's a question in the chat. Are the vertices in the are guaranteed to be unique? And it looks like Subendra answered and said, yes, in one set, the vertices are guaranteed to be unique.
Yes, that is correct because it is a set. So a set cannot have repeating elements. So hopefully, if the student has more questions regarding that, I'm happy to answer.
So are you using the C++ set implementation, standard library implementation kind of?
We don't have to because
Right.
the set are collected from the random walks. And I can't do random walk on a visited vertex while doing the random walk. So by construction, it is unique. But even if it is not unique initially, this second algorithm treats everything as a set. So there cannot be repeats. So each set has unique item. However, a single vertex can be part of different set.
Gotcha. Well, thank you.
Okay. So our first line of action is to find the vertex present in most number of RR sets. Well, in implicit representation, that becomes very easy. We just have to find the vertex with the largest tag array that tells what were the distinct IDs of the RR set that they belong to. So we find a local argmax by going through their local information. So each processor gives their voters. Processor 1 says, hey, I think vertex 1 could be influencer because it was part in 3 RR sets, which is the largest I can see. Processor 2 says, hey, it's 2. That was found in 5 RR sets based on my local information. Processor 3 says, that is RR set, that is vertex 3. That was found in 4 different RR sets. Now these processors need to communicate and decide one winner, and that winner can be found using an integer all reduce operation. But now, instead of sum being the reduction operation that we did in my previous example, we can do a max operator to find which vertex is the global winner. And why can we still use max in all reduce and not violate any correctness guarantee is the primary requirement for a reduction operation to be correct is the operator we are using needs to be binary associative. Summation is an associative operation, so is max. Hence, the output of max is also correct. Like we are seeing in this example, vertex 2 wins because vertex 2 was part of the largest number of RR sets, which is 5. Now, all processors now agree upon that. So what's going to be our line of action? Now we have to remove all the RR sets vertex 2 was part of, but we don't have RR set stores explicitly. So we are going to go through every single vertex locally stored in each processor, and whichever RR sets vertex 2 was part of, we now have to subtract that RR set. So set of vertex 2 is the set of basically 1, 2, 3, 4, 5 is basically 5 RR set vertex 2 belong to. We now need to remove this footprint from all processors. That means processor 2 now has to send that information, that array, may I say, of 5 elements to processor 1 and processor 3. And to do that, we use a broadcast operation that I went over rather quickly. But what are we broadcasting? We are broadcasting, in simple terms, an array of length arbitrary that we do not know beforehand, just processor 2 knows. So we perform the broadcast 2. Let's say that length of the broadcast was length of the tag array that we named in our paper for vertex 2, that now every processor has a copy of because we perform the broadcast operation, which is an operation for one processor to let every other processor know some information. Now, we are going to remove the footprint of RR set 1, 2, 3, 4, and 5 from every single vertices RR set information. So that looks like this. Sorry for my choice of colors. It should have been red. Whatever is highlighted in green is actually being removed. So we are going to delete this information. And after that, we are going to repeat this process with the deleted set of information or the next iteration's input. So if these RR set information stored implicitly was my input for iteration 0 of select seeds operation, the next one that we get after removing the footprint of RR set 1 to 5 is the input for iteration 1. And we are going to repeat this k times recursively. And that way we get our k-influencers. Now, from a parallel computing point of view, there are a few challenges to it. Now, the majority of the communication is happening in the broadcast step, which experimentally we found is not as bad. It's more than a single integer, but it was far, far less communication intensive than the previous best known algorithm in literature. So that scales just fine. But the problem is the integer max operation and the broadcast operation both incur their individual latencies. And the whole computation we are doing in between these communication steps are very load imbalanced or irregular, in the sense that some processors might have to delete a lot of information from their local RR sets, and they might take a lot of time, while the others did not have to remove that much information, and they were done within few milliseconds. And that's a fundamental challenge of this BSP style of parallel algorithm, where we decompose a parallel algorithm into set of independent local computation followed by a global communication, and that keeps on repeating. So the processor must synchronize 2 times k times, and within each synchronization, there is a variable amount of work each processor is doing, which may lead to performance issues down the line, maybe. So the question we were targeting while trying to write this paper was, can we do anything better? So my idea was, can we introduce a new data structure? And let's try to walk through it. So we are going to introduce IMM 2D algorithm. And why 2D? Because so far we are working on linear size data sets. We had a set of RR sets that we are operating on very linearly. Let's expand that linear operation into a quadratic size data structure. So I would need some more faith while explaining this, that the example I'm going to show you is going to scale to everything. We are going to introduce something called a co-occurrence matrix. And what does this co-occurrence matrix do? If entry I, j of this co-occurrence matrix says something, for example, here, element 2, 3 says the output, the data stored is 3. That means on the left, we will find 3 different RR sets where vertex 2 and 3 of the input graph coexisted together. So RR2, RR4, and RR5, in my example, are 3 different RR sets where we saw vertex 2 and vertex 3 of the graph coexisted together. And we do that for every pair of elements stored in the RR set. So we find what are the pair of elements stored in one RR set, do a +1 in the equivalent entry in the matrix. And we keep doing that for every pair of vertex in each RR set and get this matrix called co-occurrence matrix. Now, it could be really long because it's quadratic in size. However, since we realized the matrix that we generate is sparse in structure, we can still get away with doing this without blowing up the memory very badly. So we now construct a sparse co-occurrence matrix. The operation we do here is akin to a many-to-many operation, but we do this asynchronously. And that means we need a single synchronization step to be able to do so. Once this matrix constructed, we have a distributed count array that was already stored just by analyzing the RR set that told me how many RR set each vertex was part of. Now we are going to follow an algorithm to essentially do the same operation we did with vertex removal and finding an influencer, removing RR sets, and repeating the same process, but without changing any data structure significantly. So this is our count array, which tells each vertex is part of certain number of RR sets. Find a global argmax using an all-reduce operation. 2 happens to be that example. So 2 is our first influencer. Now we use this identity where we take the second row of this matrix and subtract that from this array C, which is our count array. This process can happen without any communication if the matrix is column distributed among processors, like I'm showing in color coding here. And after that, I get my new C array, which is the input for iteration 1, if the original C array was input for iteration 0. And if we repeat this k times, we'll get the exact same outcome of the operation we're doing so far via set subtractions. Now, some of the feature of this algorithm that I discussed. The construction part is the extra pre-processing step we are doing. It takes extra memory. It's not quadratic time extra memory in practice, but it is more memory than linear storage of just the sets. The communication volume of this asynchronous operation is very high. We synchronize only once, but we are still doing a lot of communication. And then we query this matrix k times using a single integer all reduce operation, which, although has latency, and that is a problem, scales very well because it's a single integer operation, and all our communication libraries are very efficient at doing so. So we wanted to see how much time each part of this algorithm was taking, because the second part could be a bottleneck. We ended up seeing that it's not a bottleneck. Let's ignore the result of 6,000 processors because that was beyond the strong scaling limit of the input we are looking into. What we see here is the yellow part, which is the construction phase, takes almost all, if not all the time of this algorithm. And the query phase, or the k iterations, where we're iteratively looking through this data structure, it takes almost no time. Now, this is one of the plots that you are supposed to reproduce to see what happens when you are, instead of looking into thousands of processor cores, looking into hundreds of processor cores, what observation you have. Now, the communication runtime, this is for you to look into later. This can help you analyze what you are going to observe in your experiment. I'm not going to go over it for too long. I'm almost also about to end the meeting time, so far behind. Next thing that you are supposed to plot in your reproducibility result is how does strong scaling look like? So here, each plot has 4 software. We are going to make you focus on just actor IMM 2D and actor IMM or actor IMM 1D. And we are going to make you keep the same input and increase the number of processors, double it every time, and show and make you plot what's the time takes in each number of processors for the same problem. This shows us how scalable an algorithm is. And the trends you see can be explained fairly well using the runtime analysis done in the paper itself. And the last one that we would want you to explore is what happens in both actor IMM 2D and 1D algorithm when we increase the number of influencers you want to query each time. So as the k, which is the number of influencers to query, increase from 64 to 1,000, how does different algorithms behave and why? And my suggestion would be, again, look into the runtime analysis of each algorithm, and that will give you a lot of hint. And if you observe something that defies that, that's all the more reason to talk about it in your explanation. With that being said, I am done. I took a long time. I will hand it over to Shubh unless somebody has other questions just from the slides.
I want to thank you, Subhadra, for breaking down the information in a complex topic and making very, very accessible. So thank you. Great work. I just have a quick question. The matrix is always symmetric, right?
Matrix is symmetric.
Yeah.
We make sure it is symmetric while constructing.
Mm-hmm. And are you using any compressed representation to store it?
No. The idea is compressed representations can help, but focus here was on the communication part. That doesn't get help much in compression. And we have enough memory with some of a lot of processors that we did not need to compress.
That's right. Any questions for from any of the teams? This is a good opportunity to ask about a question.
Right. So just because earlier you mentioned that the matrix is stored as a sparse matrix, right? Am I right?
Yes.
So there's some sort of compression already, I would presume.
There is compression in the sense that we are not explicitly storing the zeros.
Okay.
But even then, there are more clever ways to compress a sparse matrix, which is already there in inference maximization literature, which we did not explore in this paper. But in the sense that we are not storing the zero, yes, we are storing the matrix in a compressed format.
Okay, and another question is, sorry if I didn't catch that earlier, but how is the original graph stored?
Original graph?
Yes.
So to store the input graph, which is, let's say, the left picture in this slide, you can store it in any way. Shub can correct me. To best of my memory, we stored it as a COO representation, where we store the graph as an array, distributed array of u comma v, where vertex u has an edge to vertex v.
Sorry, could you repeat again?
It is stored as a COO representation, where
Uh-huh.
whole graph can be thought of a distributed array of pairs, where each pair u comma v represent a single edge between vertex u and vertex v of the graph. And
okay,
we
got it.
distribute those pairs to all the processors to store the graph.
And also just to clarify on the challenge, so we are supposed to re-implement the algorithm by writing our own code, or
You are supposed to run our code on your machine.
Oh, okay.
Get the plots for the runtimes, and your job is to explain what you observe. If it is same as the paper, explain in your own term why that is so, and if it's different, explain what you observe is different from our set of experiments.
Super. In that sense, do you think it's a good time to go through the document that you put together to explain the challenge? I think that that will help.
Yes. Shub, I'm wondering if you wanna take over that part, or would you like me to do it?
Sure.
Please.
Sorry, so I'm not aware of the document part, but then I'll go over to the demo part like real quick. If I think it'll take max 2 to 3 minutes just for the people to understand what's going on. Yeah. So so we choose between.
No worries. So I'll start sharing.
Sure.
Give me a second.
Yeah, it'll take me a lot of time to access that document.
No worries. I have it open. I just need to figure out I share the correct screen. The one for students, not for the graders.
Yeah.
Okay. So this is the documents that will be shared with you soon. That summarizes the problem, which I gave a brief overview about. And the challenge is following. Your first task is to implement the runtime library we used on top of MPI that you need to be able to run our SC24 software. Second task is to now install the SC24 software, and we have a quick small input for you to test if the installation is correct and it's working or not. Next is the figure 6, which is the strong scaling figure. So given these 3 input, SOC opinions, COMDBLP, COMUTube, publicly available graphs, you are supposed to run ActRMM1D, ActRMM2D algorithms end-to-end execution and plot them with increasing number of processors and analyze and describe what you observe. And why so? The why is quite important because quite often than not, the trend can be explained from the runtime analysis done in the paper. Next is figure 13. Here, we are making you reproduce the same thing. In ActRMM2D algorithm, we saw there was 2 phases, the matrix generation and the query that we're calling it K-loops. What fraction of the total rhyme in the select seeds algorithm in 2D is spent in each phase. That's something for you to look into. That's what you will be observing here. And the last one is to show 1D and 2D algorithms, how much time they take on the same input, which is the same to CompDB, LP, and CommUtube here, when we increase the number of K, which is the number of influences we are querying from the graph. So as that keeps on increasing, what happens to the overall execution time? So these are the three main computational tasks you have. Be able to run it and explain the trends results you observe on the input graphs on your machine. And the two minor task is for you to be able to even install and get this system up and running. Yeah, feel free to also stop me at any point if you have any question. This is important for you guys to have a good idea about, so you don't get tripped by doing it.
And as Suvadra says, William and the app experts, Suvadra and Spender will share out these instructions soon to all the teams. But in the interest of time, we're at the end of the hour, we're a little bit over. Let's have the little short demo and then maybe give some time if people are available for some extra questions.
Sure. All right. Okay. So I'll go ahead and share my screen. Okay. Please let me know if the font sizes are okay, because yeah, let me just okay. Oh wow, okay. Jesus Christ. Okay. Wow, where did it go? Okay, perfect. Okay. I think it's good. Yeah. Okay, so the very first thing is what I'll do is just quickly run through the repo.
Can you make it a little bit bigger,
yes.
please?
Yes, let me just. Okay. Is this fine?
Worked for me. I don't know.
To me.
Okay, perfect. Okay, so I think the very first thing is the input file. So what we've done is we don't want you to go through the whole process of converting the graphs into a zero labeled or one label, starting one labeled vertices, as well as it contains the weights which generally Stanford website doesn't contain. So we have already converted it for all of you guys. So I think as so we describe, you're going to test it on CommDBLB, CommUtube, and SSC opinions. Then we have the scripts as usual, which you can run to set up. And finally, coming to the code, which is available in the source directory, where LT just represents the generic configurations of files that are needed for both the algorithms. LT1D, where generate_rr.h was the first kernel, selectseeds.h is the second kernel, and production.cpp is the main is the sort of the driver program for both. And similarly for LT2D, which is generate RR. Yeah, don't go by the naming. This is generate rr.h and selectseeds2d.h, and the same production_2d.cpp is the driver program for both. Okay, so I'll just quickly. Okay, I think yeah. Oh, something's not right with this. Yes. So we are in LT1D right now, and what we're gonna do is we're gonna first run. Yeah, I'm gonna just quickly change these parameters. I'll just quickly explain these parameters. So we are running a script on slump-based clusters right now. So what does it mean is there are 4 nodes that we are running on, and don't worry what are nodes. I'll just explain in a bit. So imagine that you have a box, and inside those box you have 24 cores, 24 CPUs, like you can assume analogously, because our system doesn't sort of go into the multi-threaded fashion. So imagine that you have a one box analogous to a node where you have 24 cores within. So what I'm saying to the program that you have 4 nodes that is denoted by capital N, and the small n which denotes the total number of cores. So 4 into 24, that's going to be 96. Then this is the executable production. -f flag is for basically asking you to input your input graph or the data set. So right now it's available in our Scratch directories, which is kind of fast because of the Lustre file system. -k flag represents the number of influencers that you want to select. So we want to select 100 influencers for now. -e represents the approximation ratio. So remember that this algorithm is not is not I mean, it is deterministic algorithm in that sense, but it is also an approximate algorithm. So it won't give you, the problem is NP hard. So we won't be able to verify whether our solution is correct or not. So hence we have an approximation ratio, which is -e, which is represented by 0.13. So what does this imply is your -e is nothing but the failure rate. So you're going to eventually have a success of 100 minus 13, 100 minus 0.13% of the guarantees there. And -o is, okay, so -o is nothing but it'll represent all the influence of vertices that are selected, and it'll store it in a file. So yes, if you like just count the number of lines in inf.txt, that's going to be similar. That's going to be exactly same to 100. That's the number of influences that you collected. And -t time.txt, which is just another flag for us to help you reproduce the figures. And -c, which is nothing but the cyclic distribution inside the graphs, which means that every vertex is going to be stored as vertex modulo the PE number, and there it'll be the vertex will belong to that particular PE or core or rank, whatever is analogously sort of understandable. Okay, so I'll quickly run YouTube. This is for 1D algorithm, and you can see how the different steps happen. As Suvi explained, that one is generate RR followed by select seeds, and the delta per PE is nothing but the number of RR sets that you're collecting per rank. So this is nothing but 1376 multiplied by 96. So you can imagine that it's already taken a hit with respect to the number of RR sets that we have. It's pretty huge. Coming to the second step, again, it happens, and then the last step, which is 366, and it finally ends here at somewhere around 10 seconds in total, or 9.724 seconds in total. So this is for 1D algorithm. I think someone has a question. Could you maybe quick how to share the build process and dependencies? Yes. How do we enable OpenShimano?
Yeah, let's repeat the question for the recording. I'll just repeat it out loud. Could you maybe also quickly show the build process and talk a bit about the required dependencies? Do we need to enable OpenSHM and the OpenMFPI config? Sorry, I stumbled on my words a little bit.
Sure. Yes, I think let me just quickly run over through 2D algorithm, and then I'll just like quickly make the program for you guys, and I'll just show the script as well, which makes it so we are not like hallucinating meanwhile. Okay. So yeah, so as you just saw, if you're in LT1D, then that directory just contains production, whereas if you're in 2D, you're just gonna append a _2D flag there, and yes, we should just simply run it. Same flags, and now you can see the difference that it's almost 9x or even bigger than that. Like the total amount of seconds that it takes is 0.374 with the same number of iterations, same steps of how to generate the RR sets and the select seeds and so on and so forth. If you notice the time taken in matrix gen and in K loops, so this is the first, followed by the second, followed by the third. So you'll be able to see the accumulative time taken in phases of matrix gen and K loops at the last, which is nothing but 0.238 versus 0.015. So you can clearly see that a lot of time is being spent in generating the matrix rather than just querying the data, querying the table as Suvi mentioned. All right. Yeah, I think I should probably focus on the build part for now. So I'll just remove the directory. Okay, let me just quit the notes.
I guess, Shubhendra, we don't necessarily need like a live build,
Okay.
but perhaps maybe talk a bit about the required dependencies.
Okay.
Do we need to enable an OpenSHM and the OpenMPI and in the OpenMPI config? What are your recommendations there, or what are the dependencies that you're working with?
Sure. Okay. I can quickly explain the dependency. So I think we have 3 modules here, which you can see at the top, which is GCC, I think, which is definitely going to be there in your configurations. Then Python, which is required for us to install, and then OpenMPI module. So a question was asked that do you need to enable OpenSHMM in OpenMPI? I think OpenMPI intuitively offers you the OpenSHMM capability. So I don't think there's going to be any additional flag that you have to support to get it running. OpenMPI should support SHMM as well.
Should let me add one thing. So I think the question is that when you build the OpenMPI from scratch, I think should we enable the OpenShift flag? I think the answer is yes. Maybe the easiest way to install the OpenMPI with OpenShift enable is the SPARC. Maybe you could do the SPARC install plus, sorry, the SPARC install OpenMPI plus the OpenShift flag. That should be okay. But we are very happy to support if you have any questions and issues.
Sure. Okay. I thought that we would be giving them the OpenMPI module at the end of the day. But okay, if you guys are definitely installing it from scratch, the OpenMPI module itself, then yes, you would need to enable the support for Shmem as well as Dr. Akito told. Okay, then I'll just quickly go over to the dependencies. So our HClib runtime system, which is what is the prerequisite for installing the SC24 software solutions, is the two libraries. One is known as Bail, which is nothing but the aggregation library, which is helping you communicate beneath. So this block contains the first prerequisite of installing our runtime, followed by our actual runtime on the top. Which wraps around this aggregation library and helps you enable programmability and productivity into the semantics. Finally, we have a library known as trng4, which is nothing but a parallel random generator library. So it's a very easy build for trng4 as well. So these are the three library dependencies that we have. And then finally, you would be able to, and yeah, there are some export flags here, which you definitely need. For example, Bail, all of them are most likely related to the LD library paths. But a couple of them, which is important, is export HClib workers equal to 1. Yeah, and I think rest all are just simply indicating to the files that we indicating to the lib files that we sort of have. Yeah, so talking about the prerequisites, we only have 3 libraries that you got to install it. They're pretty neatly installed on probably every production grade system. And after that, you should be able to simply just go here, HClib and source, and then whatever you want to compile, say this, and then just simply do make. And you're going to get this huge chunk, which is nothing but, yes, it's compiling all of our prerequisite 3 libraries inside, and it's just simply made. Yeah, so please feel free to ask me any questions, and yeah, I'll just pause here and probably wait for the questions.
Yeah, I think that was great. Thank you so much, William, for bringing us all together here, and Subhadra for taking a deep dive into the inner workings of the algorithm in the paper. Subhadra, that was super useful. I think on behalf of all the student teams to see go through the repository and also just see how it's run and understand what the output looks like. Are there any questions from people attending? Yeah, I know we're a little bit over the hour, but let's take a time. If you guys want to take advantage of having the authors here and the Repro Challenge share, please feel free to ask a question and mute yourselves or drop something into the chat.
I think no one else has a question. I just want to say thank you also, Lemay, for enabling us on the SCC, and Subhadra, thank you so much. We really appreciate all your effort and for the challenge. And whenever you have a chance, if you can upload your slides or the documents that you have. So
I'll pause the recording